で、時間になりましたので、始めたいと思います。今回ですね、非常に注目されている方多いと思いますけども、Zenohっていう新しい通信プロトコルが、出てきまして、開発は多分3年ぐらいやっていると私は認識してるんですけども、そちらの、開発を牽引されているZettaScaleの CEO、CTO を務められていますアンジェロさんがちょうど日本にいらっしゃるという機会がありましたので、私になんていうんですかね、しないみたいなことを、言われまして、だったらぜひこういう、イベントをして、日本の皆さんに知ってもらいたいなということで、こういうイベントをさせてもらいました。で、聞いたことあるっていう方は結構多い、結構今、このZenohの知名度って上がってきてるなと思っていて、聞いたことあるっていう方は多いと思うんですけども、使ったことあるっていう方は、例えば会場だとどのぐらいいらっしゃいますかね。Some guy can use have experience to use Zenoh.
Oh. So like Superman.
っていう感じで、これからちょっとすごく気になっているっていう方が多分オンラインの方も多いと思いますので、その、イントロダクションですね、導入のところを今日は特に、ご紹介いただきたいと思っています。で、大体プレゼンテーション40分していただいて、その後ディスカッション20分というつもりでお願いしていて、ますけども、多分すごく、ディスカッション盛り上がるんじゃないかなと思ってますので、ちょっと状況を見ながら、進めていこうかなと思っています。ということで、お願いします。Please start presentation.
I can set
your presentation will be 40 minutes.
Yes. Yeah. Okay. So first of all, thank you very much for the invitation, because I informed you not even 2 weeks ago that I was coming to Japan, and we said, let's do something. And, it was incredible. So thank you very much. Thank you very much. So I'm Angelo Corsaro, ZettaScale CEO and CTO, and today I will try to introduce you to Zenoh, okay? And hopefully after this meeting you will be able actually to program some Zenoh, because the idea, we are computer scientists, right? Okay, so let me tell you a little bit more about myself, real quickly, starting with what I've done and decrypting my name, okay? And AI is very popular now. so actually this image was generated by AI, and the only things that I did is put my name and my surname, and I said let's see what it comes out with. This is what it comes out with. And yes, my name really is Kaizoku Kenshi. Kaizoku Corsaro, but a good one, because Corsair or Corsaro is a good pirate in Italy, and so this is what an AI thinks how I should be. I don't know if it matches. I cannot show the wind during the day, okay? Anyway, so besides being a Kaizoku Tenshi, I'm a telecommunication engineer, so I graduated from an engineering school in telecommunication in Italy, and then I did a PhD in computer science in the United States. And in 2002, I was one of the 3 persons that actually started back then the DDS standardization. So I've been working on protocol for most of my life. That was always what passionated me. And among other things, I am actually the guy that invented Zenoh. So I invented the Zenoh protocol, and I did the actual first implementation. The first and the second, I contributed. First, I did it all. The second, I contributed massively. The third, I contribute a little bit less, because I'm also now the CEO of the company, so unfortunately, I can do less programming. But I still supervise, and I'm very much involved on the technical matters. So what was the problem that we wanted to solve with Zenoh? So we've been working for in previous incarnations of companies in distributed system for quite some time. And we were some of the early company working in, for instance, smart cities. So we did the Connected Boulevard project in Nice. I think it was already 2009, 2010. And in that system, we had, for instance, 2 key applications. One was parking, and the other was trash collection. Because in Nice, during the summer, the population doubles. And so there is a huge problem of trash collection, because you get overload of trash, 40 degrees Celsius, and you can imagine the smell. And as it is a place where you usually go for luxury vacation, bad smell and trash around is not really nice. And so the idea was, let's put sensor in the trash can so that we can have smart collection of trash can. And the other was that, again, especially during summer, because of the heat and because of the traffic, 30% of the parking spots are unused, but it takes you well over 30 minutes to find a parking place because you don't know where those are. And so that increases emission. And I don't know if you have the same problem here. Maybe you have the same problem here in Tokyo. When it's hot, you have a thermic inversion. So all the gas go back in your head and the air quality gets very bad. And so that was an example where we had a very small sensor connected through a low power network, and then we had some edge devices and eventually a data center. And the problem was that when we were trying to build those systems, what we were ending up was something like this, a digital Frankenstein, because there wasn't a single protocol that was able to go from the microcontroller up to the data center and perform. Okay, so you have to stitch together multiple protocols. Not to mention the problem related to data storage, because most of the solutions are cloud-centric. It makes it easy. You store everything in one place, so there's only one place where you have to search. But for this kind of application, you want to decentralize the storage. But if you decentralize the storage, the problem becomes, how do you know where to look the data that you have stored in a decentralized manner? Things were even more complicated when we worked on another smart city project along with Cisco, Schneider, and a few other companies in Barcelona in 2015, where in that case, we were trying to have a completely decentralized solution, and the problematic of the storage and decentralized storage was very severe. Because today, in order to query data, you need to know where is the database, right? So there is no location transparency, and only once you know where is the database, you can issue a query. Not to mention distributed computation, okay? And so this was the kind of system that we were building. And if you go back in time, actually, in the beginning of the internet, we had a very similar problem. So there is an analogy today. In the days of ARPANET, okay, if you recall, different campus and different companies were using different protocols. And IP actually was invented as the protocol to interconnect different networking protocols, different local area network protocols. And this is the original IP paper. IP was intended to the protocol gateway between different protocols that they would use for local area network. But if the internet is what it is today, it's because in the end, IP became the one protocol used across the internet. Okay. And so the question is, okay, but if we have one protocol, that's IP, are we done? Well, no, for various reasons. The first and more important is that the IP protocol is host-centric. Okay? In IP, you need to know an address in order to communicate. And that creates all the problems that usually we have to deal with when we have to deal with mobility, with fault tolerance, with load balancing. And the other important aspect is that our applications are usually data-centric, right? When we open a browser, we don't think what is the address of the server of the page I'm looking for. We put the name of the data that we're looking for. And so there was a proliferation of protocols creating data-centric abstraction on top of IP, like MQTT, DDS, and a few others. But again, all these protocols were solving part of the problem in the entire puzzle. And again, trying to go end-to-end required lots of integration. And again, these protocols were solving the problem related to data in motion through PubSub, weren't solving the problem related to storages and distributed storages. And this is when, around 2015, I just, said, why don't we try to solve this problem? And it was interesting because back then, obviously I'd done lots of work on DDS, and I'd also been working for a few years with a pool of European experts on NDN, Name Data Networking, sometimes also called intent-centric networking. And the basic idea of those protocols are data-centric protocols for distributed queries over the internet. So those protocols solves the problem of keeping data decentralized and querying from anywhere. But then if you try to use them for distributing data efficiently, so for data in motion, not so easy, not so elegant. And so I said, what if we try to blend the two? and come up with a protocol that puts the two concepts together, so that we can unify data at rest and data in motion. And the result was Zenoh, which is in fact a pub/sub query protocol because it blends the two concepts. And you know, there is a saying that says all great discovery happens by chance. So it wasn't our objective to abstract distributed computation. But when we, you know, after a few iterations, we realized that actually the mechanism that we were using to represent distributed source of data could represent both the reading out of a database, okay, or something that in any case answer queries. But the query can look into a database or can trigger a computation. And so with the same mechanism, we were able to represent distributed queries as well as the triggering of distributed computation. And we will see how that works. Okay, the other interesting things is that so besides the unification from one protocol, right, that can run from the microcontroller to the data center for data in motion, data at rest, and computation, and you have location transparency. So you don't need to know where the producer of the data is for pub/sub. You don't need to know where the storage is when you issue query. You don't need to know where the computation is when you trigger computation. You just name what is in your interest, and our protocol, as we will see, routes the request. Okay, so what is happening around that? So what is the adoption? What are people saying? So all of our community runs on Discord, and I will have the link to Discord in the last slide. We have a Zenoh server. And these are some of the messages that from time to time you see. This one is actually from the CTO of the construct, which is the leading ROS2, let's say, educational entity. This one actually is from the architect of a company that has been using Zenoh to build a distributed analytics platform that works along with the crypto. So the basic idea is that you make available hardware so that third party can run heavyweight analytics, and you are paid back through crypto. So the crypto is called crypto wrapped, and they have this distributed analytics platform. And I think he was the first one to realize that Zenoh can be used as a Kafka for edge computing, right? And as we will get through, you will see the reason. Amazon earlier this year wrote an article in which that's Richard Elberger, which is the head of IoT ecosystem at AWS IoT. He was looking at pipes protocols that are used today for IoT. So he was looking at MQTT, MQP, DDS, and COPE. And so for those of you that are not familiar, for instance, COPE, the Constraint Object Application Protocol, was introduced by Cisco precisely to work in the constraint device and constraint network. But then it's not a protocol that you can use on a data center, right? So again, we go back to the digital Frankenstein. So he was looking at all these protocols that work in some scenario. And then his conclusion was, well, perhaps the most viable protocol that will help us mature toward the ideal model for IoT is Eclipse Zenoh. Yes, Zenoh is open source and hosted as part of Eclipse, which, as you know, is now a European open source foundation. So that means clear governance, open governance, and we are the main contributor. We are the inventor of the protocol. Sorry. But if you look on our repository, there are quite a few contributions from external as well. And anybody with sufficient contribution can become a committer. So it's entirely meritocratic. Okay. Other interesting things, later in September 2022, was a recommendation from the focus group AI for autonomous driving. And that was the focus group on data protocol for automated driving safety. That's a specification which was studying all different protocols available on the market and was supposed to come up with a recommendation of the protocol to standardize for Europe for intelligent system communication. They looked at many of the protocols and they were struggling with one problem. What was the problem? The problem was the following: the digital witness. Imagine you have two autonomous vehicles, like here, this car and this little truck here, that crash into each other. Okay, so computer typically don't lie yet, and so if you look at the reconstruction of the environment, maybe in some instances you won't be able to understand who caused the actual accident. Okay, and so you will need witnesses. But witnesses won't necessarily be people. Witnesses will be other autonomous cars that also have reconstruction of that environment, potentially infrastructural element like a camera, like a smart cross light. And so if you look at this problem, it's easy to express the solution to this problem with a query, right? It's a spatial temporal query. I can define the volume, I can define the time, and the data set I'm interested in. The problem is that I have no clue who has an answer for the data set. How do I get it? And that's where Zenoh comes into play with its geo-distributed queries. So in Zenoh, it's trivial to solve, and that's what we demonstrated. And thus, the recommendation by the TU to use Zenoh for intelligent transport systems. Another place where Zenoh is used today is the India Autonomous Challenge. So this is the first drive of the car that's being teleoperated, like when you teleoperate across the Pacific Ocean, your robots, right? A very cool video, by the way, yes. And again, this is interesting because here it's teleoperated over a Cisco Universal Wireless Network. It's a special wireless network. Every car has just 1 megabit per second of bandwidth, and there are some additional limitations. These cars are powered by ROS. So inside the car, there is DDS. But if they try to use DDS over that network, it kills the network. They dropped a Zenoh router with a DDS plugin, done. Okay. Some other example of adoption. This is an autonomous train called Lucy. Again, built on Zenoh. And yeah, a few other things. So remaining in robotics, there has been an interesting, let's say, crescendo of adoption of Zenoh, because the DDS was designed to work on fixed network. Okay, I think this is something important to be understood. When we designed DDS, the target of DDS were combat management system, right? Were system, let's say, mission critical system in which you have lots of resources, reliable, fixed network, and symmetric systems that are well dimensioned. Okay, DDS wasn't designed to be used across wireless network, wasn't designed to be used at internet scale. And if you look at the very nature of the reliability protocol, right? In DDS, if I'm a data writer, all of a sudden, I have to keep state for every matching data reader, which means if I'm a small device, the amount of memory that I need to use, right, depends on the number of readers. But on an open system, I don't know. So that just cannot work. So either you break the semantics or it cannot scale, right? And this is one of the reasons why we invented Zenoh, because DDS was, once again, works quite well in a given scenario, but if you try to move it to use case for which it wasn't designed, no, doesn't work. And that was the problem that people in robotics were experimenting when trying either to scale with lots of topics, or scale over wireless network, or communicate over wireless network. So there was a first evaluation, and this is actually a presentation that you can find on our YouTube from the user meeting, Zenoh User Meeting on June 2022. That was a presentation from the Open Robotics CTO that did an evaluation and said, Zenoh looks like a new hope for robotics. And which were some of the very interesting results. As they were struggling with DDS discovery, right, one of the things they wanted to evaluate is the relative difference of the amount of discovery generated by Zenoh for the same ROS application. Some of these were Mont Blanc, for instance. And I think this is the most interesting graph. In blue, and this is in percentage, okay? So 100% is all the traffic, and then you have the percentage of actual user data and the percentage of discovery. So this is for Zenoh, this is for DDS. The difference is huge because here you have 2-3%. Here you have anywhere from 35, 40 to 50%. And in this case, there is so much discovery data that nothing that gets through. And that's when the system gets overloaded because of discovery, you can't discover, and okay. So this eventually led to a formal evaluation, okay, of protocols. There is, in fact, if you search on Google RMW alternate, this is the keyword, you will see the announcement of the selection of Zenoh as the protocol to be used in alternative to DDS. And this is being implemented by Intrinsic as the main contribution of the next release of ROS. And obviously, we are supporting their development. it's a super interesting report because they looked at the bulk of the protocols that are available on the market. They made a very systematic assessment, and there is a table where they rank all the requirements provided by the community, and the Zenoh comes on top. Not only that, they also asked the community what the community would like to have, and the answer was Zenoh, of which honestly we were surprised because it's a young protocol, and so obviously we are very honored of this result, and we are starting to feel the pressure now, as you can imagine. And it's interesting to look at this table because Zenoh number 1, number 2 is TCP ROS, which is what ROS1 used to use because that works, right? And you see all the protocols that were suggested and evaluated, so it's quite interesting. Okay, let's go back to Zenoh, okay? Because in the end, it's good to see what is happening, but let's go back to technical matters. So we try to give some intuition of what Zenoh does. Let's look how it sits on a networking stack. So as we wanted to, okay, first of all, the bulk of our software is implemented in Rust. Why Rust? Because we care about security, we care about safety, we care about performance, and more important, we care about abstraction. Okay? So the very first implementation of Zenoh was written in OCaml. I know that Japan is very popular in the functional programming language. OCaml is a functional programming language. I love I stopped teaching during COVID, but up to COVID, I was teaching functional programming in a grande école in France. So yeah, so we were an OCaml shop, and we rewrote it in Rust, essentially for a couple of reasons. Some of our users were complaining because it's harder to contribute if you don't know OCaml, and there are not so many OCaml programmers. The second issue that we had was that multi-core support for OCaml was supposed to come next year. And that was already 2016, 17, 18, it just came this year. And we felt that Rust was now ready for us to move to it. And so in 2000, it was 3 years ago, we started a complete rewrite in Rust. Okay, so the bulk of our development now is in Rust. But we have bindings in C, C++, Python, JavaScript, and TypeScript. If you are interested, the binding is already on the ZettaScale repository, will be on the Eclipse pretty soon. Rest, C++, Kotlin, with full support for Android. Okay, so if you want to use Zenoh on Android, we have a nice Kotlin binding and the build system. You have built-in support for shared memory and zero copy. You don't need to use any external dependency. And our shared memory implementation is distributed. Okay, so there is no centralized daemon, neither a centralized shared memory segment that all the process mess around with. We can sit as low as the data link. Okay, so as such, we can run on serial link, on plain Bluetooth or OpenThreadX, but we can sit on or raw Ethernet. Okay, so we are about to release the raw Ethernet transport. That's quite useful also for TSN. We can run on top of the network or on top of the transport. So at this level, we would run on top of TCP/IP, UDP/IP, or a TP5 is still someone has an implementation and does a transport. For all of any of you that recalls TP5. Yeah. And again, our wire overhead is 5 bytes if you configure for minimum wire overhead. In terms of support, the embedded version runs almost anywhere. And by the way, the embedded version is called Zenoh Pico. And as of today, that's implemented in C. Why C? We are actually expanding the portion of Zenoh Rust there is no STD, so that we can run even bare metal on an ARM. So that's eventually our dream. But as of today, still the embedded ecosystem is mostly driven by C. And so if you want to run on Arduino, ESP32, Embed, Zephyr, Natix, whatever, you can use the Zenoh Pico. And for automotive, we already have integration of Zenoh Pico and Microsoft. Okay, so let's look at what are the topology that this protocol supports. So we wanted to remove constraints, right? And so Zenoh allows you to communicate in peer-to-peer using, for instance, a click. And if you think about DDS, this is the model that DDS takes, right? In DDS, there is the assumption that every application can directly communicate with every other application, either because you're leveraging UDP multicast or because you have one-to-one unicast session with everyone else. But this doesn't work if you have a fleet of robots platooning, maybe with a radio network. Because in radio, we might, if we don't have line of sight, or if depending on the networking technology, maybe we cannot communicate that. And so being able to support mesh networking is very important, and Zenoh can do this. Okay, but then sometimes we have application even today in robotics in which some of the robots are so constrained that they cannot afford to forward data for on behalf of other peers. And that's because of computing, that's because of battery, okay? Because more I/O means consuming more battery. In that case, they can take the role of a client, and client can pair up with just about any peer and use the peer to forward information to the interested parties, okay? Client can also be communicating through a router, that in that case would be as a simple broker. And then, obviously, you can deploy a router as you will. Our router are software router. I mean, conceptually, it's like an IP router for a data-centric, an end data networking protocol, but it's software. It's quite lightweight, and you can run it. I mean, usually people run it even on constrained robots, okay? And you can run it on a Raspberry Pi without any problems. Okay, so if we compare to other technologies, to go back in perspective, right? MQTT supports only this model. In MQTT, publisher and subscriber communicate through a broker, and that introduces the challenge of where do I deploy the broker? So the broker usually is in the cloud. So even if I have two devices that are close by, they have to communicate, for thousands of kilometers with the cloud to reach the broker, only to then go back to the device, which, hey, we were close together. Why are we generating all this entropy, right? That's not good for the universe. And on the other hand, DDS assumes a click. So all of a sudden, that with all the advantages and the consequences, then frees you from topological constraint. Use the topology that makes sense for you. Okay. Other things that I want to point out is that the routing in Zenoh, although we are not publicly exposing the plugin, it's pluggable. So as of today, you can choose on your Zenoh subnetwork the routing that you want to use. Okay. So if you are under this assumption, for instance, you don't want to use link state, you don't need link state because you don't have a mesh. Okay. Here you want to use link state, here you want to use link state. So whenever, and that's a runtime configuration. Okay. And we are going to make, for those that are passionate about routing algorithm, we're going to make public the routing plugin API, so that if you have specific application on specific topology, you can implement your own routing. Okay, so there are lots of innovation that we are doing in this area because we think that will be an innovation unblocker for researcher and also for industries and also for ourselves. Okay, because depending in different portion of your system, you might want to use a slightly different routing algorithm and compose your system this way. So that would be quite powerful. Okay. And we already give a hint by supporting today two different routing protocols. Okay, the other thing is that the main difference today, okay, between a peer and a router is that a peer, as in this scenario, can route data, right, on behalf of other peers, clients, and so on and so forth. So in that respect, has the same logic of a router. But the difference is that a peer has end user application. A router doesn't. What does a router provide? The router, on the other hand, has a well-defined plugin interface that you can use to integrate third-party protocol so that they can be routed through Zenoh, okay? Or integrate storages. So we have storages plugin, and these are the storages that you will be able to query in a distributed manner, okay? Once again, you take existing storages like InfluxDB, RocksDB, Amazon, S3, Minio, main memory file system. As we will see, you are able to keep data stored there, but then query from anywhere on the network without knowing where the data is stored. Okay, because that's again the key principle of the Zenoh protocol. And these plugins, as you see, we have a plugin for DDS, now a specific plugin for ROS2, which is quite efficient, plugin also for MQTT. So for instance, if you have an MQTT application, you could deploy it using routers, and all of a sudden have the MQTT broker close to your application, and have as many as you want, and then have Zenoh route information within them. All of a sudden, you can use Zenoh as your backbone of information, and then use the plugin system to integrate brownfield systems that are using other protocols. And again, implementing a plugin is quite straightforward. The Minio plugin, for instance, was contributed by the community, okay, which is a good example of something that is not so hard to do. Okay, how does it perform? So this is an evaluation that was performed by NTU, National Taiwan University, and on their on a 100 gigabit network. And what you see in light blue is, and that's a throughput test. So light blue is Zenoh peer-to-peer. So you have a publisher, a subscriber, and they are publishing data from 8 bytes to 512 megabytes, okay? And here you have the throughput in a logarithmic scale, okay? So this is Zenoh peer-to-peer. This one is Zenoh with a router in the middle. So you have a publisher, a router in the middle, and a subscriber. And that's to see the impact of a routing hop on the throughput. This is DDS, that's Cyclone DDS, that is our DDS implementation. And then this is MQTT, and this is Kafka. So iPerf on this network has a limit of 70 gigabit per second. And the peak performance then reaches 69, and that's for 8 kilobytes. You have 69 in peer-to-peer. I think it's around 48 through a router. DDS is at 17 gigabit per second. MQTT, it's at 2 gigabit per second MQTT, 3 gigabit per second, no, sorry, 2 gigabit per second Kafka, 3 gigabit per second MQTT. And then MQTT has this drop here, which apparently is a known problem that MQTT has with dealing with large data. At least the Mosquito implementation. So in terms of performance, throughput is quite incredible. And if you look at the latency, by default, with the default configuration, you get 10 microseconds in this network. If you enable ultra low latency, 6 microseconds, but then your throughput will go down because all of a sudden we don't do network scheduling, like to improve the throughput. And compared to 25 microseconds latency for MQTT, 75 for Kafka, and 8 for DDS. So you see DDS has lower throughput. There is clearly a trade-off on latency versus throughput. But in Zenoh, a little bit higher latency, but incredibly, so you get 3 times of the throughput. And then if you activate the ultra latency, you get faster latency too. Okay? Okay, let's see what is the programming model. So in Zenoh, everything is a resource, okay? And a resource is just a key and a value, okay? Then you can denote set of resources by identifying expression on their key with wildcards or double wildcards. The double wildcards will expand to an unlimited number of nested level. And then you can have selectors. A selector allows you to select a key set with a key expression, and then have here a series of parameters with argument and value, where some parameters are built in on Zenoh. Okay, and are specific to our storage implementation that you already get off the shelf. So in the case, for instance, you have a sigma operator, so the selector, the where clause. So here I'm looking for CO2 greater than 12, and a pi operator databases. That's the projection. Okay, so project humidity. So in that case, you will only get the humidity for the temperature sensor whose CO2, the air sensor whose CO2 is greater than 12. In terms of abstraction, you have a publisher, which again is a source for data or resources whose key matches a given key expression, a subscriber, which is a sink for values whose key matches a given key expression, and then you have a queryable, and a queryable is like a well. So in a well, you go with a saw to take water, and a queryable is the same. A query says, look, I'm a queryable for this key expression, okay? So anything that matches this key expression, come to me. I will have answers. Okay. In terms of primitive, obviously you have open close declaration. Some declaration are optional. So declaring a key expression on a publisher is not required. Those are just optimization, okay? Optimization because it gives us a way to map the big key name into small integers. And to do that, and to force us to do that. If you don't declare the key expression or the publisher, then it's the Zenoh protocol that has heuristics that will decide what to map to integer and when to do that, okay? But you have a way of forcing that mapping by using declare key expression and declare publisher. Then declare subscriber, you need to do it in order to declare a subscriber, and so declare subscription, and declare queryable. You need to actually do that in order to declare a queryable on the network. And then the way in which you operate, you have put to produce data, delete to delete a resource, pull to pull data, because subscriber can be pulled subscriber as opposed to push. So in that case, it's you that whenever you feel like consuming data, you will consume data, and the get to issue a distributed copy. Okay. So one reflection on that. So if you look at the abstraction that Zenoh provides, they are universal with respect to what you need in distributed computing. Because in general, in distributed computing, you need to move data around, and for that, typically use PubSub. You need to store data and eventually query this data. So you need to deal with data in motion, and you need to trigger computation. And so PubSubscribe is trivially supported in Zen, right, by its PubSubscribe support. Remote computation can be represented by queryable, because all of a sudden, a queryable is a generalized form of computation, which is also location transparent, right? And we will see how that works. And a storage is nothing but a combination of a queryable and a subscriber, because a subscriber can be seen as the writing half of a storage and a queryable the reading half. And that's precisely how we implement our storage plugins. Okay, so how do you program Zen? And I will be providing you with some example in Rust. So in Zen, we support both synchronous and asynchronous programming API, okay? And all the API uses the builder pattern. So if you want to know what are the options for a subscriber, search in the documentation for subscriber builder. You want to know the option for a put, search for put builder. Everything is done with builders, because that way your application will always be backward compatible. Any innovation will be just a new option on the builder, won't impact your existing application, which is important. And this is also the reason why there is this strange res that you see often in our code. That's to resolve a builder and execute the operation that you are trying to craft, okay? So how do you select between the synchronous and asynchronous API? And I will be showing you example in Rust, okay? So those of you that know Rust, good. Those of you that don't will be at least a primer in Rust, okay? So you select to use the synchronous or asynchronous API by simply importing the right prelude. So if you use Zenoh prelude sync, then that's for synchronous application. And if you include Zenoh prelude, this is an escape, okay? Because async is a reserved word. So R pound async, and that's a prelude for a synchronous application. And where you see the difference, well, the difference is that in this case, after the rest, I just unwrap, and here I have to do the await, okay? And I can use this as an asynchronous application. How do you publish data in Zen? Trivial. Once you have a resource, a session, which we opened like this, and this is the default configuration. You can read the configuration from a file. You can modify the configuration on the fly. Deciding the transport you use, or if you are a peer or a client, or the routing, it's all done through the configuration. Okay, so it's nothing in your application code. So if you want to publish some data, that's as simple as having a session, calling the operation put, passing the key and the value. And I'm writing a string. Yes, Zen understands strings. Okay, but not only, as we will see. If you're doing recurrent publication, then it's better to declare a publisher, because in that case, you are guaranteed that when you declare a publisher for a key or a key expression, this will be mapped immediately to a small integer. So with every publication, the string will never go on the wire, but there will be a small integer that is unique within the session. You don't see it, you don't need to decide it, we assign it automatically, but that's what we use on the wire. So you get the efficiency of a small integer, And usually that's only 7-bit, unless you have more than 127 resources on a given application, on a given session. And if you have more, then it will become 14 bits. Okay. Anyway, so you declare a publisher. Again, you resolve it, you wait for it, and then you can put, just by putting, in this case, I'm putting a video frame, okay? And that's it. So Zenoh natively understands a series of values. Okay, so in Zen, you can natively put integer, JSON, float, strings, octet, and then you have built-in support for a series of a JSON for a series of MIME types. You can define your own types, so in that case it would be app custom, and so on and so forth. So now imagine that you have a temperature sensor and you just want to write the temperature. In Zenoh, you can write the float that represents the temperature. Okay, and that's how you do it. For instance, in this case, I'm writing a float, a string, an integer, an octet sequence, and a JSON. And on the other side, actually, even if you don't specify the encoding explicitly, because I'm adding this line just to show you how to specify the encoding, you will still perceive it as a JSON. We will do the automatic transformation and will give you a JSON object. Very handy. Okay, the point is trying to make it simple for you, right? How do you subscribe to data? Well, you subscribe like this, so declare subscriber and with a key expression, done. But then you get back a string. And so that's then the beauty of asynchronous programming, because you don't have to, you can pass a callback if you want. There is also an API for callback, but I mean, I don't suggest it because you have dependency version. In this case, we have a string, and you see I'm iterating through a string like if it was a container, which is very elegant, like we do in functional programming, right? That's an asynchronous string. Here, I'm receiving asynchronous data. So whenever there is a sample, I do what is called a deconstructing assignment, as we usually do in functional programming, but you can do it in Rust. Okay, so, or you can call it pattern matching too, because it's, yeah. So if that's the result, as you can see, if I receive a sample, then I'm going to print the sample. And it's great because this is asynchronous code that looks completely sequential. And for us, it's much simpler to reason when we look at sequential code than callback and code scattered anywhere. And all of a sudden, because it's a stream, I can use higher order programming, right? I could do things like map, filter, reduce, and so on and so forth. So that's quite nice. Okay, let's finish with query and queryable. So a queryable, as we saw, it's something around the network that answers queries. And query that match a key expression, and it answers with a finite stream of key values. Okay, that's what it does. How do you declare a queryable? So you use declare queryable, you define the key expression, and then you need to decide if this queryable is complete or not. So a queryable, right, through the key expression is defining a set, logically, right? And this is a set that is denoted. So being complete means that actually it will have answer for any of the elements denoted by this set. If you declare that it's not complete, okay, it's like a non-complete function. It means that there are certain holes, okay? It's important to distinguish between these two cases. And these holes have nothing to do with consistency, okay? It's just the fact that if you're representing a computation and this computation is not complete in your data set, right? In this set, you are not defined everywhere. So you have holes. I like to think about it is like cheese, okay? If it looks like an emmental cheese with a hole in the middle, it's not complete, right? Because in your set, there are certain values for which you don't have answers. Otherwise, it's a complete set. And you're able to distinguish this. And then when you issue a query, you can decide what is your target, how you want the data consolidated back, and that's it. And you will receive a stream of reply. So here the reply that you get is just, once again, an asynchronous stream of replies. And you're able to detect when the query is completed and also detect when different queryable that matched have completed their sub portion of the data. And I think this will become clear with an animation. We're almost there. So in terms of query target, there are different ways. There is the best matching. The best matching represents the bigger intersection and the closer in routing term. You can use all, so all the queryable that have an intersection, all complete, so all queryable that are complete or complete n. And just to give an intuition, complete n is key if you want to build quorums on top of Zenoh. If you are familiar with the idea of quorums for strong consistency, that's why we need complete n, okay? Could also be for voting systems. So imagine this application here issues this query. So get Zeta webinar Zenoh start, and it targets the best matching. So on that side of the network, the best matching might be this one. Okay, why? Because it has the bigger intersection, because this is complete and this is not. So bigger intersection. So in this case, it covers that. And it's the closest in routing term. And if I issue the same query from there, actually, this queryable will be triggered. Because once again, I mean, we are not pinpointing one entity. We are doing set operations, right? And routing based on that. Here, I'm asking to target all querybles. So in this case, all queryable that have an intersection with my query will be triggered. And notice that this one and that one are not triggered because they don't have an intersection. By the way, apologies, but there was a typo here. You should read only 2T, not 3, okay? So believe it's 2, although you see 3. Sorry for that. And if you search for all complete, then only this will be triggered, okay? And if you search for complete 2, then actually, this is a good one, because in terms of routing, actually that one would have been closer. But depending on the routing policy, maybe we decided to go that way. Okay. And then the consolidation, you can decide not to consolidate at all, or to ensure that through every routing path, you will get monotonic consolidation, which means if there are replicated key value, we will remove duplicates, and make sure that you receive only the latest key value for each key. And if you use latest, then in that case, we ensure that across all routing path, you will only receive a data set that represents to the latest value for every single key that was part of all the reply that you got. Okay? And so you can go from known, which has you might get lots of data and you have then to clean up duplicates depending on how you issued your query, to latest, where obviously we do more work in the infrastructure to filter everything and filter as soon as we can. Okay, I want to finish 3 more minutes with QoS and then we are done. So in Zenoh, reliability is declared by the subscriber. So the publisher doesn't decide the reliability. It's the subscriber that decides if he wants to receive data reliable or not. And then the infrastructure will behave accordingly. Okay. What the publisher control is congestion, and you can control that for every single sample. Okay. So you can decide whether a given sample should be discarded under congestion, or if we should block the application if we detect congestion and if we are out of resources, protocol resources. Okay. So when would you want to use blocking versus dropping? Well, anything that is real-time data, right, and produced periodically, you might want to be able to drop. If you're doing video, it might also depend on the encoding, right? Because there are certain frames that are very important, so maybe you want to block for those. Those are major synchronization frames, and anything in between could be dropped. And the nice thing is that in Zenoh, sample per sample, you can decide what should be blocking versus dropping, okay? Or you can set it once for all for equipment publisher. You can control priority, And we do scheduling based on the priority. There are 7 levels of priority. If you don't do anything, the default is data. And then the highest is real time, the lowest is background. Once again, you can set the priority for every single sample you publish if you want, or associated with the publisher. And I think we should probably stop there, right? Because we're out of time. Yeah, yes, because so let's conclude. So as a team, we are, I think, trying to remain very innovative. We have more idea than time to work on our ideas, which I think it's still good. You will see that in the slides that you will receive, there is also a section on liveliness, which is something quite powerful that you can use to do group management, internet scale, okay, that we've added recently to the protocol. There are more things that will be coming up, quite interesting, one of which is access control, okay? So today you can have authentication, and we have 2 different mechanisms for authentications, okay? One of which is based on TLS and MTLS, another one which is a plugin of our session establishment. We are coming up with actually a better implementation of zero copy and share memory. So there is quite a bit of innovation. So innovating at fast pace, the community is growing. And last week, there was also this announcement or this presentation from General Motors that was showing how they selected Zenoh for You protocol. So you can see the presentation on our user meeting. And again, if you like our technology, just help us spread the love for the Blue Dragon, the Blue Dragon protocol. So thank you very much again for the invitation. It was for me a great pleasure.
Yes. すごく盛りだくさんで、ちょっと時間足りなかったなってすごく後悔してる。We don't have enough time to understand Zenoh because Zenoh has many interesting features. So we need more time to understand with hands-on training. Yeah. I think so. So, ですけども、ちょっと時間は時間ですので、質問とかはちょっと、別に延長して。
By the way, if anybody wants to do some coding now, I'm happy for it. We can. Should we?
時間は別に厳密に区切ってはないので、質問とかあればぜひお願いします。あと、すみません、資料、コンパスの方に上げてましたので、そちらも見ていただきながら質問いただくといいかなと思います。日本語でされましたら、頑張って英語にしようかと思っています。遠隔の方はチャットでも構いませんけども、どなたかどうでしょうか。
Simple question.
Yeah.
What does Zenoh stand for?
Zero Network Overhead Protocol.
Fast.
Oh, sorry.
Zero.
So zero network. Let me show you. So this is zero network overhead.
Overhead.
Yeah.
Okay.
Okay.
Understand.
Yeah. And also without the H is the name of the philosopher. And again, it depends how you write it, because in some cultures you write it with an N. And so this recalls the N. There are various games in the name. Yeah. But the acronym is Zero Network Overhead Protocol.
One simple question.
Yeah.
Why is the image of Zenoh from Dragon?
Okay. So, and by the way, so I have to share something, because if we look at Zenoh protocol, I want to tell you the story of our logo. Okay. So the first logo actually was this one. Okay. And this logo was drawn by myself and Olivier. Olivier, you probably, you will see it on Discord and on our commit. And it's a weird dragon because it's a dragon with a horn, right? Usually dragon don't have horns, because we wanted to give Zenoh a logo of a mystic animal. So when we were thinking about the logo, the first logo we had come up with was an narvalio. The narvalio is this strange fish with this very long horn. that lives often in the Arctic. It's like a white dolphin, but it's super long horn, and nobody understands what is the purpose of this horn, okay? But then it was looking too much like Docker. And so I said, okay, no. But we like the horn of the Narvalian. And says, okay, another mystic animal and powerful, right, is the dragon. The dragon is wisdom, right? Because many people think the dragon, dangerous fine. No, the dragon is about wisdom. I'm a tiger, but I wish to become a dragon one day, right? And so we did this dragon, but we put the horn of the Narvalian there. So that's the story, and that's the original dragon. Then the dragon that you see today was done by a designer based on this, okay? But that's the story of the novel.
It's a good story.
And this is now the dragon, right?
はい。温めていった感じですか？質問ありますか？
Yeah.
日本語で。はい、頑張
And
ります。
let me ask you one question. So I hope that you understand. I mean, when our comics, they are really meant to be comics. And so you really have to read them with the comics idea, right? So here, for instance, he always talks with a robot because it's the protocol used by robot to talk. Okay? Yeah. And you see, this is the logo, and then we have humanized to make it a little bit more fun. So we have actually one comics per month. And you saw that we made one of the dragon going to Japan, right? Have you seen it? I will show you. I will show you. Yeah.
Yes, it's the dragon in Japan.
Yeah, yeah.
あ、どうぞ。ここで。はい。
製造業のソフトウェアに興味があるんですけども、OPC-UA のプラグインのサポートとか計画に入っていたりしますか？
He's one of the experts on
OPC-UA?
industrial
Yeah.
domain. So he's curious about the support of OPC-UA. Do you have a plan to support OPC-UA protocol?
Or already supported it?
Okay, so OPC-UA, we did a binding for a customer, but that's private. It's not open source. Okay, it was under a contract. Yeah. If you look on our Discord, we get a request quite often to do an OPC-UA plugin.
Yeah.
We will do it at some point. Okay, but I think before the OPC-UA, we'll probably do the Canvas plugin because we have even more requests for Canvas. But that would be quite nice. And there are some OPC-UA open source implementation. So yeah, it's on our list, on our to-do list. Yes, absolutely.
Yeah. 他にありますかね。私はパフォーマンスが非常に気になっていて、I'm so curious about the performance. I understand Zenoh is super fantastic compared with MQTT, DDS, and so on. But why?
Okay.
I can't catch up the actual reason.
Okay. So
Yeah.
yeah. So I think MQTT wasn't redesigned for high performance, right? So I think that's easy. It's just the protocol. DDS was designed for high performance. So the interesting question is, why do we perform better than DDS? And I think there are a couple of points. The protocol is much simpler. Okay, actually, let me show you because I want to show the protocol structure so you get an idea. Because I have a presentation, just a moment. Because that will be, I think, quite interesting for anybody that likes protocol. Yeah. And yeah. Oh. One more moment, because then I will be able to give you the proper articulated answer. But I wanted to show the difference in wire messages. Oh, here we go. here it is. That's what I was looking for. Because I have a full implementation on also on power efficiency.
Yeah.
But again, we couldn't cover everything. Okay, so even MQTT. First of all, MQTT, here the topic name is a string. And when you have to parse MQTT, actually, you cannot do a single pass. Depending on the message type, you have to do 2 passes. That already takes time. Okay, so, but again, if we look at DDS, so the protocol is quite complex, and the amount of wire overhead is quite a bit. Okay, and then in DDS, you send individual messages. So this is a full DDS message, right? So you already have 4 bytes for the magic, other 4 bytes for protocol version of vendor ID. You have another 12 bytes for GUID prefix, and so on and so forth. Okay, and then you have to eventually you get to the data, but even in the data you might have inline QoS, and the encoding, I mean, is often articulated. Okay, so let's look at the Zenoh packet. So first of all, in Zenoh we send frames. Okay, so a frame, well, actually, I'm showing here a frame that contains data, but a frame can contain different kinds of Zenoh messages. A frame is just a collection of Zenoh messages. Okay. And then when a data message has this shape, so 1 byte error, if the resource, you recall I told you, if you register a resource or declare a publisher, all of a sudden on the wire, we just send a small integer. That's the integer. Okay. Or if it's not an integer, it can be a combination of an integer representing a prefix and a postfix that can be either another integer or a string. Okay. But in the optimal case, is an integer. So we have 2 bytes, then the length, and then we have the payload. This is trivial to the code.
Standard.
Okay. And so if you think about the throughput, all of a sudden, our implementation tries to make sure that we send the frame with as many data messages as possible. And in terms of the wire overhead, this is how it scales. So if we have n messages on a frame, right, all of a sudden, we tend to a wire overhead of 3 bytes. So there is outgoing code, single pass. The fact that the protocol is simple, it means that there is good affinity with the cache. Because in the end, the simpler you are, right, the better you have cache affinity. So the amount of code to decode that versus the amount of code to decode that is different. And that makes a huge difference with respect to cache affinity, which makes a huge difference with respect to performance. Okay? We can pack more user data and less overhead. So there are a series of reasons why Zenoh is performing so well. There is just not one, but it's a combination of factors.
Yeah.
And you know, simplicity is very hard to get.
Yeah.
It's a lot of work. We didn't get it at, it takes iteration, but simplicity has value.
Okay, understand.
Is that any RFC standard or?
No, and and again, what we plan to do is that there are a few more changes in the protocol that will slip in before the end of Q1, and then we'll put a stamp of version 1.0 of the protocol. And we will write a specification of the protocol, but no standard bodies. We want this to remain open source, open specification, because otherwise it gets too much politics. Okay, and we want to be innovative, open, and we think the open source is the best approach. And we've had already 2 universities implementing Zenoh. One did an FPGA implementation of Zenoh, University of
Cool.
Yeah, and another one is doing an implementation for PLCs.
Oh.
Yeah, and today you read the code because we used to have a specification that we wrote, right, of the protocol, but there were too many changes, and so we said we retire it. So if you look on the Wayback Machine on the Zenoh.io a few years ago, you can still find the PDF, or I can send you. But the protocol has changed quite a bit, and we will do an open specification with version 1.0. But today, the source of truth is the code. And then we have a Wireshark plugin that you can use to easily dissect the packet and learn how the protocol works. And we have an Elixir API, right? Contributed by.
I have some question.
Sure.
On the protocol side.
Yeah.
The overhead and header is very simple, but I have no idea how Zenoh can deal with packet when the Zenoh deployed on top of the data link.
Yeah.
How to deal with that issue.
Okay. So as of today, right, the way in which we deal with reliability is by using reliable transport. And if we have a best effort transport, then we do best effort. In terms of reliability and resent, there are the protocol message to deal with it. The sequence number is in the frame. Okay. So that information that you require is here. And so if we lose a frame, we resend the frame. And the other important thing is that the reliability protocol, okay, is not between a readers and a writer. The reliability protocol is between two session endpoints. So you can have a zillion of publisher and zillion of subscriber is just reliability session. In reality, it's more complicated than this. The reality is that a transport, okay, so let me really tell you how it is. Okay, so we have transport. Each transport can have multiple links. Okay, and so if we take as an example the TCP transport, each link, right, will be used to send data. And if you're using multiple priorities, right, we will do priority-based scheduling to make sure that the higher priority data gets sent first. Now, the reason why we use multiple links is because on long-haul connection, if the two of us are communicating with just a TCP/IP socket, if there is network congestion, it takes a lot of time to recover from the NAGO and the backoff. If you are using multiple TCP/IP connection to communicate between you, that's a good approach to recover much faster from congestion, because it is as if you have a send window that is much wider.
Yeah.
And that's one of the tricks that we also use. Okay, but then in terms of reliability, there are the mechanisms to implement reliability on top of best effort transport. But we don't do that today. I mean, this is one of the things that we have to put in place. Okay, because today, I mean, people either use TCP/IP. If they want reliability over UDP, they use QUIC. We have a transport for QUIC. And then if we have best effort traffic, we use UDP. Okay, but the mechanisms are in place. And eventually we will put it. But today we don't have a burning need for it. Okay, but there is another point also. Reliability. Can I use the board? Real quick? Yeah. No, because there are. Okay, I want to give you a more precise answer. Because and I love this because in France now there is the this one I love. Okay. So imagine this is an application, and then here router 1, router 2, router n, and this application. Okay. I was using a square for applications. So the default Zenoh reliability is hop to hop. So I have a reliability from here to here, and reliability from here to here. That's the default reliability. That means that and again, I did this because it's an arbitrary graph, but this is the routing path that we use. This one crashes, then my communication might be rerouted, but I lose potentially some packet or I get duplicates. But that's the default reliability. What we have is also end-to-end reliability. So that's optional. You have to call in. Why? Because that requires maintaining more state. Right? Because all of a sudden, we need to maintain some state here. And so by default, the reliability is hop to hop. So if you don't need to be reliable in presence of crash, that's okay. You can tolerate that. That's very efficient and super scalable, because all of a sudden, I can have 1 zillion subscriber here. I just have to do one reliability session, which is very scalable. If you then need end-to-end reliability, then we have end-to-end reliability. And how does that work? It works like in NDM. Okay. So what is the principle of NDM? That you have caches all around the routing path. And the data that is sent is cached for some time, okay? And so if there is a failure, and on top of the caches, there is some additional state that is added here, okay? And so whenever there is a failure, you can detect here that you are missing some sample from here. Send a NAC, and this NAC will be served. So in this case, for instance, will be served by this one. Okay, if we were a little bit more lucky, well, in this case, tough luck, because, sorry, no, in this case, it will be potentially served by this one, if he has it, and if he doesn't, it will be by this one. Okay, and you can also decide potentially to have this cache in the application, but that takes resources from the application. So if your application is constrained, you forget, and you just have the caches on the infrastructure. And this is precisely what NDM do to repair loss.
Great.
Yeah, because you see, always going back to the source puts a lot of pressure here and introduces latency.
So to deal with that topology change, I think the Zenoh router needs to get the capability for the dynamic routing.
Yes, let me show, because we do that.
As you said, you have a 2 plugin for routing.
Yes, so when we do, so let me show that live. Well, live, that's one of our tools that visualizes Zenoh routers. So I think that would be interesting.
Almost.
Yeah, I will be sharing. Sorry. And so if you want to experiment with this, it's called NBFT reliability. It's on a branch and will be merged quite soon. Okay, it's on a branch because we have not designed, we were not entirely in agreement with the API, but it will be merged as in the next release. NBFT reliability.
NBFT.
Yeah. Non-blocking fault tolerant reliability. That's what it means. Okay. Okay, so this is actually an older version of a tool. This tool is not open source, okay? And it illustrates a few interesting things. So you can actually establish a session with any router, and through any router, you discover all the router in a Zenoh network. And then you can visualize the routers, okay? So this is the routing graph that was discovered by our administration space. Because in Zenoh, anything, so there is an administration space that gives you information, allows you to gather information about a specific router, the topology, and as you could see, additional information, like who are you connected with, what are your plugins, and so on and so forth. So if I move forward, you see you have statistics on the amount of traffic. Let me go forward. And if you start application are discovered. So you see, this is a publisher. There is no data going through because no subscriber has been started. And as soon as the subscriber will be started, And then essentially you will see, we will start killing routers, you will see the rerouting. Let me move forward because this was Olivier making a presentation. Yeah, so you see the application, the subscriber has started, and now you see the route which is going and the amount of data that is flowing. And by the way, in this case, he is streaming a video of himself. Okay, this is what the application is doing. Yeah.
Streaming over Zen.
Then yes. Oh, yeah. Okay. And then what it does, well, it plays around because we have some API to do migration, so it will migrate the application. So you will see this application moving. Okay, you see? So look, it moved, and then it's rerouted immediately. Go back a little bit. Okay, now we force a migration. Boom, you see instantaneously it's rerouted. And then we will start killing routers, but without any suffering, of course. Okay.
I think you know the ICM guys.
Yeah, I mean we've been giving tutorial at some of the I think even in the ASEAN Japan conference last year with a tutorial on Zen. Still migrating, and I think now we will start stopping routers. Let's see. Let's move quickly forward. Yeah, he migrated the other application. Oh, here we go. Okay, now he kills this router. Look. You see, it's rerouted. Well, okay, and well, as you talked about video, sending video with Zenoh, it's actually quite straightforward. So, yeah, we need to go. We need to go. But this is for instance, and I can share this code if you want. No, I opened the wrong file. I moved the wrong window. Anyway, this is the right window. Yes. So you establish the session, declare a publisher. This is the utility function that we have. You capture the frame and just put it. Once this is over, I can run it and let you so stream video over there.
One question from Zoom
Yeah.
chat.
Yes.
His question is about zero copy feature.
Yes.
Could you share any recent progress or current status regarding the zero copy feature?
Yes. So let me actually show some code to answer the question. So we already have zero code, okay? And in order, you have to enable the shared memory transport. And then the way in which it works. So let me increase the screen.
Please share your screen.
Oh, I'm not showing my screen on Zoom.
It's correct.
Oh. Desktop too.
It's
Okay.
great.
It's my mouse. Okay, so let me show. Oops, here we go. Yeah, that's great. Perfect. So you enable shared memory transport, and then what you do, there is this shared memory manager. So you create a shared memory manager, and you decide how much memory you should have. Okay, and then using zero copy, it's pretty trivial because you allocate out of the shared memory manager. Okay, you do, and again, what you see here is that allocation can fail. If it fails, I mean, this is an example. I mean, we are waiting sometimes, and then we're issuing a garbage collection and perhaps a defragmentation. Okay, and then if you manage to allocate a buffer, then we are putting some data on the buffer, and you just write it as if it was a regular buffer. So what happens under the hood? Whenever a Zenoh session is established, so suppose we are doing an application. So we are establishing a Zenoh session. Our session establishment will do a challenge to try to figure out if we're in the same memory domain. Because being on the same host is not sufficient, right? We could be on different memory domain because of different containers or different zones and so on and so forth. So if we are on the same memory domain, then whenever I have a put and Zenoh detects that the buffer that you are passing is from a shared memory allocator, then it will send you, using Zenoh, only the information on how to access this buffer. So this buffer might be, 1 giga, whatever, will send you just 100, it's around 190 bytes message to how to get this buffer. And then we use the Rust type system to do the memory management. So whenever you drop, the reference count get to 0, and our garbage collection eventually is the activity that reclaims those buffers, okay? So that's how it works. It's supported today. Now, why are we improving this? Because the limitation that we have today is that we can do 0 copy, let's say, safely, if we assume that we are on a click. Assume, and more importantly, if there are no routers. There are some applications that some customers post to us in which on the same machine they want to have multiple routers to divide different group of applications. And in some cases, they want also this shared memory to go through routers. And so we are changing the design of the shared memory to allow for this. But the principle will be always the same. You will have a shared memory allocator with the difference that you will be able to plug your own shared memory provider. So if you are on some special hardware in which you have a vendor like Qualcomm that is providing you shared memory, or there are some other, you can have your own allocator specific to that hardware, register it with Zenoh. We at session opening will validate if we have the same provider, and then whenever sharing memory from the same provider, you still get the 0 copy. Okay, so that's in place. And the interesting part is that on the reading side, because writing side you need to see, but the reading side, there is no change. It's just a regular subscriber. You see, there is no subscriber for shared memory, because as a subscriber, you don't need to know that it's shared memory. Okay, so it's quite nice, I find.
Yeah.
Yeah.
One more question,
Sure.
but this is the final question.
Okay.
From the chat. I'm curious to know if there are plans for RMW Zenoh to support upcoming Rust version.
Well, this is what Intrinsic is doing.
Yeah.
Yes, absolutely. Yeah.
Yeah.
And there was a presentation, the user meeting.
Yeah.
The repository is already there.
Yeah.
There are already quite a few features supported, and Zenoh will be supported as part of Jazzy. Indeed, yes. Thanks to Intrinsic work. Yes.
I hope so.
They are actually advancing
Yeah.
quite fast, and we are supporting. Yeah.
It's a super fantastic engineer.
Yeah.
さあ、
Okay.
これですいません。もうちょっとお時間なので、これでおしまいにしたいと思います。改めまして、アンジェロさん、Thank you very much for your good nice presentation.
Thank you. Questions. It's always a pleasure, right? When there are questions at the end.
はい。じゃあ、これで、オンラインの方もおしまいにしたいと思います。で、会場の方は、なんか、せっかく集まりましたので、皆さんでグループフォト。
Yeah, group photo. Yes, of course. Yeah.
を撮って終わりにしたいなと思っています。で、オンラインの方はここでおしまいにしたいと思います。はい。オンラインの皆さんもありがとうございました。